Hi, I'm Bowen, and I'm glad to introduce you my autonomous learning of physical environment through neural tree search. So yeah, the content is twofold. First, I will introduce you MuX, which is the multi-color tree search-based reinforcement learning library I implemented to support the neural tree search research. And then second, I will talk about neural tree search algorithm and experiments. So first, Mux has already been released, and everyone who is interested in MuZero could try it. And also, I'm excited to announce that the DeepMind's MCTX library has listed my project. Yeah, so on the GitHub page, you could find two interesting examples that demonstrate the easy-to-use nature of Mux. Yeah. So Muax consists of 10 connected modules, which enable the general pipeline of reinforced learning, and modality gives Muax the ability to be flexibly extended. So here you can see you can define your own neural network, your own optimizer, and also your own multi-color tree search algorithm and the agent. And the wrappers gives you the flexibility to design your own environment. And also the train and test functions are defined for you to trace the performance during training and the testing. Yeah. So now let's move on to neural tree search. I will first give you the intuition about what I'm trying to fulfill. So here the agent has a map which is predicted from sensor output. And the agent could specify a position on this map, and some existing test planner algorithm would get the agent. So therefore, by continuously specifying a position on this map, the model could get the agent to explore the environment. So the key to successfully explore the unknown environment is to maintain a correct map and also a correct position of the robot. And otherwise, the task planner would give wrong actions and lead the robot to different place. And here on the figure, you can see the blue point is the goal specified by the algorithm. And the red rectangle is the agent. And you could see there are some explore area. So now let's talk about the problem setting. The settings are generally the same as the neural SLAM, but the observation is the RGB image and also the sensor pose. And the reward is defined as the exploration ratio. So, however, the action is different from neural SLAM, and it is defined as the location on the map. As the figure shows, the map is equally divided into 25 grids, and the action is exactly to map to the centric of each grid. That is, you could get the agent to one of the grid, and the path planner would calculate how to actually done that. Then we can come to the proposed method. So first, the model will encode the RGB image and also the post-sensor output as the hidden state, which are then used to generate predict map and also the location on this map. Second, the model will run multi-color tree search simulation, which is identical to MuZero to select the candidate action. And third, the planning path given the pose, the map, and also the goal from the model, and use some analytical path planner. Here I'm using fast marching method to generate actual actions. Then I'm waiting for some step for the robot to execute these actions and then collect the statistics, such as the incremental explorer ratio, and then training the agent and go back to the step one. Now we are ready to go deeper into the proposed model. Here you could see your research tree. And here the H represents the representation module, F represents the prediction module, and G represents dynamic module, and Q represents SLAM module. And you can see here for each row observation, the representation module will first encode into hidden state, and then the prediction module will calculate the policy and also the value associated with this state. And the SLAM module will generate the map and the location from the hidden state. Then it will iterate using dynamic module to simulate a real environment step. But here in the search tree, it's just the hypothetical ones. So given the initial hidden state, by the dynamic module, you will get the next hidden state. And we'll do the same thing for the next hidden state until we reach to the leaf node. Yeah. So here is an overview of the neural network for the neural tree search module. So as for representation, prediction, and dynamic module, the neural network is the same as the mu0 ones. So you could see here, the representation module takes the RGB image as input, and the image has a resolution of 256 by 256 with 3 channels. So you can see it has very large spatial resolution. So the representation module will actually reduce the spatial resolution and also to generate more channels. And the input are all scaled into the range between 0 to 1 to get better performance. And you can see here, the prediction module has the policy head and value head, each with a sequence of convolution operations, and followed by the linear layer to map it to the number of actions or the value support. And as for the dynamic module, you could see here, the action is first encoded as a panel, which has the same spatial resolution as the hidden state. And then this panel is appended to the hidden state as a new channel, and then goes through the dynamic module to produce the next hidden state. Yet as for the SLAM module will actually take one hidden state and deconvolution the hidden state to get the map and the location from it. So you can see here, the decoded state has the same resolution as the vision range of the robot. And it has 2 channels. One is representing the predicted map and one is representing the explored area. They both send to the pose estimator to generate the proposed predicted position of the robot. And now we're talking about how to train this model. So here, this is the proposed function design. All parameters of the four modules are trained jointly to match the predicted quantities from each hypothetical step to the observations from the actual time steps. So here, the predicted reward will calculate with the actual reward, and the value loss function will minimize the gap between the predicted value with the unstep bootstrapping value and the loss for my function. It will minimizing the gap between the predicted map and the actual map with the binary cross entropy loss function. And as for the post estimator, it uses MSE loss. Yeah, so here is the overview of the system. So I'm using Gibson dataset, and also I'm using Habitat platform as the simulation. Then to build the model, I choose JAX as the backend language. And also I have implemented the Nuax, which is used to implement the neural tree search model. And the output is visualized with the front-end tools. Now here, we are going to talk about the experiment. So the figure here lists all the hyperparameters, and actually has different action settings, that is 4x4 or 10x10. You would see the agent has very different performance. Now here is a generate animation from one episode. Now you can see here the agent is exploring the unknown room very successfully. And here is a comparison of the proposed model with the previous state-of-the-art model, NeuralSlam. NeuralSlam has very good performance, while the neural tree search model with 10 actions has very competitive performance. Yet the neural tree search model only trains with 30 episodes, while the NeuralSlam uses over 70 episodes. So the neural tree search model could realize a competitive result with less training effort. And you could see here the neural tree search model with 4 actions has very high variance. And I have also noticed this phenomenon. The small action size experience higher variance in performance, which could be resulted from being blocked by some obstacle and unable to make small adjustments. For example, entering a door. So about the future work and the limitation, I found that the post-estimation error would accumulate in the long run. When the robot is happen to be blocked for a long time, the predicted map could be far from correct. So I think localization need to be improved. And this is my reference. Thank you for presenting and